Okay, right please. So, right please. So in today's lecture, I'm going to start thinking about the idea of model fit, and in particular its relationship to the two quantities that we've seen already calculated by R in our examples, which are R squared and adjusted R squared. And then after we've done that section, I'll move on to thinking about complements and prediction intervals. Okay, so I'm starting there in section 1.7, so that's page 15 of the printed notes. I'm going to start off by just reminding you the definition of the residual sum of the squares, SR. So for each observation, we have the observed value, the data value, yi, and from our model, we've got our estimated coefficients, beta hat, and then the vector x beta hat gives us the fitted values for each observation. So the ith element of that vector is the fitted value of observation r. So yi minus x beta I here is the residual, the difference between the observed value and the fitted value. So SR is the sum of the squares. SR is the sum of the squares of the residuals. So the sum of the squares are the differences between the fitted values and the observed values. Now, you can think of a good fit as being one where the observed values and the fitted values are close together. So the fitted values are giving a good estimate of the actual observed values. So if that's the case, then these residuals are going to be small. We're summing the squares of them, so overall we should be getting a small answer here. So a first thought about how to judge model fit might be, well, we take SR, the residual sum of squares. If it's small, then we have a good fit. If it's large, then we have a bad fit. Now, there are a few reasons why that's a bit naive, and I'll start off with a couple of them. So, first of all, SR, the residual sum of squares, depends on the scale of the observations. So, it has intrinsic units. If you think about the units that the observations yi were measured in, if you change the units, you're also going to change the fit, because so the coefficients will change as well to adjust the change in units, and so SR will change because it has those intrinsic units. So if we want to have some sort of absolute idea of the quality of model fit, it makes sense to have some sort of adjustment to give a dimensionless quantity for our thing for model fit. And this is not a dimensionless quantity because if we divide yi by 1,000, say because we're measuring in millimetres instead of metres, then we're going to divide this bit by 1,000 as well, and so we'll divide the whole thing by 1,000,000. Okay, so SR is not a dimensionless quantity, so if we want to have some sort of absolute idea, it would make sense to have one. The other one is not really quite as important. It's more just in terms of getting something that we think about in the right way, and that is that SR, the residual sum of squares, is small if we have a good model fit, and normally if we're thinking about scoring something, we want something to be large when we're doing well and small when we're not doing well. So it would actually make sense to have a measure that is large for a good fit, whereas the residual sum of squares is actually small for a good fit. There are a couple more reasons why SR might not be such a good measure of fit, which we'll come to as we go through this section. Okay, so how can we, starting from SR, how can we obtain a new measure of model fit which avoids the two issues I've just described here? Okay. So, one thing that we could do is that we could relate the residual sum of squares to the total variation. So, say the fitted sum of squares to a null model with only a constant term. So, if we start off with a null model with only a constant term, then we probably have a large residual sum of squares. We then fit some of our explanatory variables and we reduce the residual sum of squares. So we can see what proportionate effect is that having, adding the extra explanatory variables, how much is it improving our fit in terms of how much is it reducing the residual sum of squares when we do that. So it makes sense to relate the residual sum of squares, this thing, to the total variation in the observed values. Okay? And to get something which is going to be increasing as model fit improves rather than decreasing, it makes sense to actually subtract the residual sum of squares, SR, from the total variation in the response, which is given here as SYY, it will be defined in a minute, and then we divide by SYY to give us something that is dimensionless. The total variation in the response will have the same units as SR, so if we do this, both the numerator and the denominator here will have the same units, so we get something which is dimensionless. It will be 1 if the fit is perfect, and it will be 0 if there's no improvement in the fit at all. Okay, so SYY here is what we call the total sum of squares. So this is, as I said, what we get if we just fit a linear model with only a constant term. So if we only have a constant term, the fitted value for every observation is the same, and it's the mean of the observations that we get. So it's the mean of the data, which is y bar here. So we get y minus y bar, the observed values, minus the mean of the data, and we do the same residual sum of squares thing, so we sum the differences between the observations and the mean of the observations, and we square them. And this is simply writing that in vector form. Okay? So, as I said, this SYY is just the sum of squares of the residuals in that simple model, which only has a constant term. So if our model is actually just a constant term, then SYY and SR are going to be the same, so we would get 0. And if we're fitting the data values perfectly, then SR would be 0, because the data values and the fitted values would be the same, so we would get 0 from that sum. So we would get 1 for this formula. And this is known as R squared, and we've seen already in R, at our output, that this is produced as one of the things that R gives us in its model output. Okay. So it's sometimes called the coefficient of determination, although I think actually it's most often simply referred to as R squared. It's often described as the proportion of the variation explained by the model. So you have an idea that your variation, which is essentially the SYY, the variation in the actual observed data, can be divided into 2 parts. You have the bit which comes from the model, which is dealt with by the residual sum, which is not included in the residual sum of squares, and that's the bit which is explained by the model, and then you have the random term left over, which is described by the residual sum of squares. So you start with SYY, you subtract the residual sum of squares to get the bit that's not explained, not part of the residual sum of squares, so the bit that is explained by the model, and you normalise by dividing by SYY to get it as a proportion. So that's why you can think of it in this way, as being the proportion of the total sum of squares that is explained by the model. Okay, and then the residual sum of squares itself is the unexplained part. In the special case of simple linear regression, the capital R squared, which we've just defined, actually turns out to be the same thing as the square of the standard correlation coefficient between the two variables, the explanatory variable, the x's, and the observer variable, the y's. Okay? I'm not going to prove that in the lectures, however, one of the exercises, not one of the start ones to hand in, one of the other exercises in exercise sheet 1 that asks you to prove this fact. In the case of simple linear regression, the definition of capital R squared turns out to be the same thing as the square of the correlation coefficient. Okay? So that suggests that we can think of big R squared as a generalisation of the square of the correlation coefficient to a more general sort of model. Okay. So I've already seen that it lies between 0 and 1. It's a generalisation of the square of the correlation coefficient for two variables. So that means it's sometimes called the squared multiple correlation coefficient. Although again, I think most of the time people actually just refer to it as R squared. So if we look back to the output that we got from our linear model when we fitted the tractor data, if you look back to that, you'll see that it says multiple R squared. So the R squared actually immediately comes out of the R output that we've already seen. And that will show you some code. So because R actually tells you the R squared value, you don't need to use the code that I'm going to show you very often, but it might be nice to just verify using this code that the formula that I've just shown you does indeed give the thing that R calls R squared, multiple R squared. Okay, so what are we doing here? So the tractor data needs to be known to R. So the maintenance costs in the tractor data are the column mate, and we're defining that to be Y. So that's the first line. In the second line, we're calculating the total sum of squares, SYY. So that's the sum of the actual squared values themselves minus 17 times the square of the mean. The 17 here, remember, is the number of data points. That's why 17 appears in the calculation. Okay, the residual sum of squares, we've already seen how to calculate that. We get the residuals from the model that we've fitted, and we square every entry in the vector, which is what's happening here, and if we sum, we get the residual sum of squares, and then this line simply calculates the total sum of squares minus the residual sum of squares, and divides by the total, and that gets the answer. And if you look back to the R output that we had, you'll see that that answer is the same as what R said the multiple R squared was for this model. Okay. So you don't actually need to do this in practice because it is built into R. If you look back at that output where R gave the multiple R squared, it also gives something else, which is an adjusted R squared. So I'll now show you the definition of the adjusted R squared, and I will try to explain it. So R squared adjusted. So the original R squared, we wrote it as SYY minus SR, divided by SYY. So we could just have written that as 1 minus the residual sum of squares divided by the total sum of squares. So this is similar, but it has this adjustment, which is that when we do that 1 minus, the ratio, we adjust the ratio by dividing the residual sum of squares by n minus p, and we divide the total sum of squares by n minus 1. Okay, so n here is the number of data points, number of observations. P is the number of parameters that we're fitting in our model. 1, of course, is the number of parameters that we fit in that model that only has a constant term. So in each case here, we're dividing by n minus the number of parameters that we fitted in the appropriate model. Okay, so why is this a sensible thing to do? Well, one bad thing that can happen in linear models is overfitting. So let me give you a very simple example. So imagine that we just have 3 data points, and they look something like this. Okay, so you can fit a standard linear regression to these points, and it's going to look something like that. Okay, now, a very bad thing in most settings that you could do would be to say, well, that doesn't look like a very good fit. Why don't we make a quadratic fit instead? Now, we've got 3 points here, and it's possible to fit a quadratic curve through any 3 points. So that's going to look something like that. Okay, so it's going to be a quadratic curve, which actually passes through all 3 of the points. I made it look a little bit too much like a straight line in that bit, so let me just draw that bit again. Okay, so that's actually giving us a perfect fit for the 3 points that we've got. So R squared will have gone up. For the yellow one that I did first, the straight line fit, it will have been a little bit less than 1. But for the quadratic fit that I've just done, it will be exactly 1. Okay? But unless we really were confident that there should be no random term in our model, and it definitely should be a quadratic, this is probably not a good idea. Why is it not a good idea? Because really, we've probably got some model which does have a random term in it, and we might have something up here and something up here coming in if we had a few more data points, and those would be fitted quite well by the yellow straight line, and they'd be fitted terribly by the green quadratic curve. So, unless you really are confident that you have no random term, you shouldn't try to fit your points exactly. R squared is optimised if you do fit your points exactly. The adjusted R squared that I've defined here is going to do something different. If you have enough parameters that you fit to fit your points exactly, so in my picture here, n was 3, we had 3 data points. In a quadratic regression, p is also 3, because we fit a constant term, a linear term, and a squared term for the quadratic, so we have 3 parameters. So n minus p is actually 0 for fitting a quadratic to 3 points, as I suggested you shouldn't do here. That means you actually divided by 0 there, and so you can think of this as actually going off to minus infinity, because we've subtracted something with a division by 0 in it. So this adjusted R squared penalises overfitting. If you have too many data points, if you have too many parameters for your number of data points, so P is too big compared with N, the adjusted R squared will go down to indicate that. Okay, so again we can check that in R. So using the code that I had on the previous slide, which was for the original R squared, we defined res.ss and total.ss as part of that, and there were, for the tractor data as we've already seen it, it was just a simple linear regression, so it had two parameters, it had 17 data points, so we need to divide the residual sum of squares by 17 minus 2, and the total sum of squares by 17 minus 1. So that's where the 15 and 16 in that line come from. Okay, so chapter 2 has quite a bit about model selection in it. So I won't say too much more about that now. However, as I was trying to indicate by drawing this picture, it doesn't necessarily make sense to just pick the model which has the largest R squared, because that is going to be the one which fits the data perfectly, so we just add more and more regressive variables until we get a perfect fit. And as I tried to indicate, most of the time there is a random element in the model, so we don't actually expect a perfect fit, and if we do get one, we will probably find that if we get extra data points, it predicts them badly. Okay, so the adjusted R squared is designed to counter that effect. So the adjusted R squared might be a better choice to use as a model selection tool rather than the original R squared, which if you add more variables always increases, because if you add an extra variable, you're always going to get a better fit than you had before. Okay, so that's section 1.7 on R squared. So I'm now going to move on to next section, 1.8, which is about confidence intervals. Now, there are two sections, 1.8 and 1.9, on confidence intervals, and I will quickly explain the difference between them. In section 1.8, we are interested in confidence intervals for the estimates of the coefficients. So we have our coefficients which are part of the model, beta, so it's unknown. We have estimates for them, beta hat, and confidence intervals will indicate how good our confidence can be in the accuracy of those estimates for the coefficients beta. In section 1.9, we'll be interested in a different question. And the question there is, if we have some more data, what can we say about what we'd expect to see for those extra data points based on our model? Okay, so in section 1.8, we're looking at confidence intervals for the parameters, the beta hat. In section 1.9, we're looking at predicting the values of future observations which fit the same model. Okay, so looking at confidence intervals for the beta hats. So beta hat, we've already seen, has a multivariate normal distribution. It's p-dimensional because we have p parameters that we're trying to predict. The mean is the actual values beta, which of course are unknown. That's the mean vector. And the covariance matrix is this sigma squared times the inverse of x transpose x, where x is the design matrix. Okay. Now, if we have a multivariate normal distribution, and we're interested in a single component, so for example, we're interested in a particular component of the betas, so one of the coefficients, the coefficient of a particular variable in the model, that is just a component of beta. So let's look at the ith element of beta hat. So this is the coefficient of the ith variable that we're fitting. Okay, so multivariate normal distributions components also have normal distributions, because it's now just one component. It's an ordinary univariate normal distribution. So beta hat I has a normal distribution with mean beta I, which is unknown, and its variance is sigma squared times GII. Now GII I haven't defined yet, but it's going to be the II element, the diagonal element, of the matrix which is the inverse of X transpose X. So it's the so sigma squared times G will be the matrix which appears as the covariance of beta hat at the top. Okay, so we'll call that matrix G, and GII then is its II entry, so it's ith diagonal entry of this matrix G. Okay, so that gives us the distribution of beta hat I, and we want to use that to get confidence intervals. So we can standardise, divide by the square root of the variance, having first subtracted the mean. So beta hat I, subtract the mean to get beta I, divide by the standard deviation, which is the square root of the variance, which is sigma times the square root of GII. Okay, and we know GII because it comes from X transpose X, and we know the design matrix X. Okay, so we know our estimate, beta I hat, and we know the square root of GII, which also appears in that formula. However, we don't know sigma. So sigma, remember, is the parameter of the model which gives us the variance of our random term. It's actually sigma squared, of course, to get the variance. Okay, now we don't know that. We do, of course, have an estimate for it, but to use what I've got here, that we have a normal distribution, standard normal distribution, we would need to know sigma. Okay. Now, you've probably seen before what happens when you're doing simple standard normal theory. You want to work out a confidence interval for the mean, but the variance is unknown. So what you do there, you have a similar problem. You have sigma in the formula that you use when you're standardising. You don't know sigma, so you replace it by sigma hat, which is your estimate of sigma, and then it turns out that you get a T distribution. And something very similar is going to happen. Okay, we don't know sigma, so we can't directly construct confidence intervals using sigma hat, using sigma that's here. What we need is to replace the sigma there with our estimate of it, sigma hat, and see what happens to the distribution on the right, the normal 0, 1. Okay. So we've already seen that beta hat has this normal distribution, and that it's independent of our estimate of sigma squared. And furthermore, that the estimate of sigma squared comes from this SR, divide by the actual original sigma squared, you get a chi-squared distribution with n minus p degrees of freedom. N and p here have the same meaning that they had already in this lecture. Okay. So now we use the distribution theory, and a standard result from distribution theory, which in fact you can think of as the definition of the T distribution with new degrees of freedom, is it's what you get if you take a standard normal x and divide it by the square root of y over nu, where nu is a random variable with a chi-squared distribution with new degrees of freedom. If you do this, you get a T distribution, which also has new degrees of freedom. And you need x and y to be independent random variables. Okay? So you can think of this as being the definition of the T distribution. sigma with sigma hat in the thing we had before, which had a standard normal distribution. If we replace sigma with sigma hat in that, we get something which, instead of a standard normal distribution, has a t distribution with n minus p degrees of freedom. And as I hinted earlier, you should compare this with what you get in the basic normal sample theory with unknown mean and variance. When you're trying to find a confidence interval, you can't use sigma directly because you don't know it, so you use sigma hat instead, and you replace the normal quantiles that you would have used if you did know the variance with t quantiles. Okay, so from that, we can derive a confidence interval for any particular level of confidence that you like. So 100 times 1 minus alpha percent for arbitrary alpha. Okay, so use some notation. This is standard notation. If we've got a t distribution with m degrees of freedom, then t with the subscript m and the alpha, that gives the upper alpha point, which is the same as 100 alpha percent. Alpha and 100 alpha percent are the same thing. Point of the Tn distribution. Okay. So this was too much of a mess to put on the slides, so I will show you on the board. Okay. So by the symmetry of the T distribution, 1 minus alpha is the probability that a T random variable is between the following quantile. So we've got n minus p degrees of freedom, remember, so n becomes n minus p. 1 minus alpha over 2 there, which I will explain in a minute. Then we've got our quantity which actually has the t distribution. That's beta I hat minus beta I divided by sigma hat times the square root of gii. So this is the thing which actually has a t distribution with n minus p degrees of freedom. And that should be less than or equal to the same quantile, but now without the minus sign. Okay, so we've defined these things. So this one is for the t distribution with this number of degrees of freedom, the value such that the probability that there is the random variable is actually above that is 1 minus, that is alpha over 2. Okay? Sorry, I said that right first time. It's 1 minus alpha over 2. Okay? Alpha here. Okay? And similarly here, so the probability of being less than that is alpha over 2. Probability of being here, bigger than this, is alpha over 2. Sorry, I got myself in a bit of a twist with what I was saying here, so I'll draw a picture to clarify. Okay, so here's the t distribution. Okay, it looks a bit like a normal distribution. The picture is probably indistinguishable from an attempt at drawing the normal distribution. Okay, so let's say we've got alpha over 2 here, and we've got alpha over 2 here. So the probability of being above the quantile is alpha over 2. The probability of being below minus the quantile is also alpha over 2. So if we add those two bits together, we get alpha. So the probability of being outside the range, which is given here, is alpha. So the probability of being inside it is 1 minus alpha. Okay, so this picture shows you what's going on here. Okay, so this point here is t n minus p 1 minus alpha over 2, and this one is minus the same thing. Okay, so let's take that expression over there. So we've got 1 minus alpha. So now I'm going to multiply top and bottom in the inequality by what's currently in the denominator. So sigma hat square root of GII. So we're going to multiply through by that. So we should get minus sigma hat root GII times the quantile. That should be less than or equal to now just beta I hat minus beta I, and then at the top we're going to get sigma hat root GII times the quantile. Okay, and now let's add so let's now, for the next line of what's in the notes, we're going to need to change the signs of this, which is straightforward, because if we just, this is actually just minus this and this are the same apart from the minus sign. So that's actually the same thing as the probability that the beta I minus beta I hat, so minus what we had here, is between the same two things. And that's just because this is minus this. Okay, and now, if we add beta I hat to all parts of the inequality, so this bit, this bit, and this bit, we get that this is, sorry, should be the minus sign there, beginning of the second line here, minus sigma hat. Okay, so that 1 minus alpha turns out to be the same thing as the probability that our beta I is between beta hat I minus sigma hat root GII times the quantile and beta hat I plus sigma hat root GII times the quantile. Now remember that beta hat is actually the random variable here. As usual with confidence intervals, you need to be a little bit careful about remembering what is the random variable and what is not. But this is the same thing as saying that the probability that beta I is in the interval beta hat I minus quantile and beta hat plus sigma hat root GII t to our quantile. Okay, so does that all make sense now? Okay. So that gives us a confidence interval for beta I, which is the two ends of the interval that I've just written, and the endpoints of the confidence interval. So beta I hat plus the quantile that we were interested in from the t-distribution times our estimate of sigma times the square root of GII, which came from the design matrix. Remember, G was the inverse of x transpose x, where x was the design matrix. Okay, I've done here a two-sided confidence interval, which is generally a more standard thing to do, but if you want a one-sided confidence interval, it is possible to derive one of those as well. By a similar sort of method, you could get a confidence interval for a linear function of the beta i's as well. I won't go through the details of doing that. One last point before I move on to section 1.9 is that the intervals that we've done here are for individual parameters. So you might think that if you have two parameters, say in a simple linear regression, you could have the beta 0, the intercept, and beta 1, the gradient. So you might think that, okay, you can write confidence intervals down for both of those, which you can do, using the method that we've just described. However, if you want to think about a simultaneous confidence region for the two parameters, you shouldn't think of it as being a rectangle, so just given by the two original confidence intervals for the two parameters. Okay, so in the example that I've just given, the simple linear regression, beta 0 and beta 1, your estimates of them tend to be correlated. In fact, they tend to be negatively correlated, so that a larger value of the intercept tends to correspond to a smaller value of the gradient, and vice versa. So that means that if you've underestimated the gradient, you've probably overestimated the intercept. So that means that in fact, the confidence interval doesn't look like that. It's actually in a, sorry, the confidence region of the two parameters together doesn't look like that. It's actually an ellipse. And the way the ellipse looks in the plane is related to that correlation between the estimates of the two. Okay? So that means that if your gradient is a little bit less than your estimate, then the intercept is probably a little bit more than your estimate. And so that orientation is reflected in this ellipse. Okay, so there may be situations where you've got a number which is within your confidence interval for one of your variables, and another number which is within a confidence interval for the other variable. So they both look like plausible numbers for the individual variables, but the two of them together are not a plausible answer for the two variables together. That's quite possible. Okay, so now I'm going to show you some confidence intervals for the model parameters done in R. So I'm going to use the tractor data again, but I'm going to fit a different model now. Previously, we just fitted a simple linear regression model for the tractor data. Okay, so maintenance cost was fitted as a linear function of age. So now I'm going to fit a quadratic model instead. So we're going to try and fit something like this. So xi will be the age, yi will be the maintenance costs. So yi will be a quadratic function of the age, and again we want to add on a random term epsilon r as part of the model. Okay, so the next slide we'll see the output that we get from R if we try and fit this quadratic regression to the tractor data. So we've given it the name tractor.quadratic, and we've got the summary information here. So we've got the coefficients, we've got the multiple r squared and adjusted r squared that I talked about earlier in the lecture, and we've got, of course, the intercepts, which are here, the estimate of the parameter values. So this is the estimate of the intercept, this is the estimate of the coefficient of age, and this is the estimate of the coefficient of age squared. and these are the standard errors of those estimates. So those are related to those GII terms that we saw in the calculations that we've just done. So that's why these are going to be useful to work out confidence intervals. Okay? So, for example, for the intercept, let's say we want to work out a confidence interval for the intercept. So here's the estimate, 348.088. And here is the standard error. So the standard error here corresponds to this quantity, sigma hat root GII, which we keep seeing in the calculations that we did here. So if we want a confidence interval, we're going to need to use the estimate, and we're going to need to add and subtract the standard error times the appropriate quantiles for the t distribution, which t distribution, i.e. what's n minus p here, well, 17 parameters, so it's 17 observations, 17 tractors in the data set, and in the quadratic model, we've fitted 3 parameters, beta 0, beta 1 and beta 2, intercept, linear term and squared term. So p is 3, so there are 14 degrees of freedom, r does in fact